Okay, hi there folks. We're now in our next video in number theory, and we're going to continue our video in the topic of the Chinese remainder theorem. We are finished with our videos in the existence and the uniqueness proof of this theorem. Now we're going to give some examples of the theorem at work. So one particular example, which is very close to our hearts, is the Sun-Tzu's puzzle, which we solved by iteration in the last two, three videos ago. And this time we're going to apply the Chinese remainder theorem to solve such. So let us first recall what is the Sun-Tzu's puzzle written in his book, okay, way back then in the ancient China. So the puzzle goes this way: find a number. So this number is an unknown that leaves a remainder of one. So meaning there's a remainder of one when divided by three. There's a remainder of two when we divide it by five with the same number, okay, with the same number, and the remainder of three when divided by seven. So there's a remainder of 1 when divided by 3. So this is like if we will let x be the number. So be that let's use hashtag for the number, be the number. So therefore, it leaves a remainder of 1 when divided by 3. So this is x is congruent to 1 mod 3, x is congruent to 2 mod 5, and x is congruent to 3 mod 7, which is shown here. Okay, so with this or system of linear congruences, we'll be solving this and getting the value of the x, um, naming it as the unique solution, and finding the general solution for this particular puzzle or this problem. So first, let's provide a solution here. Solution. Oops. So since the moduli, okay, we're going to take note of this moduli. Okay. Again, our standard notation is recall our standard notation is x is congruent to a sub I mod small m sub I for all in which all these m sub i's are relatively prime um, for all i's between 1 and k. Okay. Now, um, since in the moduli we can see here since the moduli which is small m sub 1 is equal to let's see here 3, small m sub 2, that's the second moduli, is 5, and the third moduli small m sub 3 is 7, and we can see that the, they are pairwise relatively prime. So they are pairwise relatively prime. That is their GCD is equal to 1. So the GCD of 3 and 5 is 1, the GCD of 3 and 7 is 1, the GCD of 5 and 7 is 1. So they're pairwise relatively prime. So therefore, we can use the central the Chinese remainder theorem. So by the Chinese remainder theorem, let's use the acronym CRT for that. Okay, Chinese remainder theorem. So the linear system has a unique solution. Unique solution. Okay. Now to find such unique solution, uh, we we need to first find we need to find the following um, big big M sub 1. We need to find the big M sub 1, big M sub 2, big M sub 3, Y sub 1, Y sub 2, and Y sub 3. All of these are or can be seen in the proof, okay, um, in the proof of the theorem. of the theorem. If you haven't seen the proof yet, so this is the perfect time for that. Kindly watch my videos, my two previous videos, showing you the proof, the uniqueness and the existence proof of the Chinese Remainder Theorem, that there exists a solution and the solution is said to be unique. So we need to find those first. Specifically, we need to find first find the big M's. So we say that to find big M sub 1, big M sub 2, and big M sub 3. Again, recall that big M as a total is the product of all the moduli. That's the big M. Big M sub 1 is the product of all the moduli save the the moduli of the first congruence in the system. So for instance, um, big M sub 1 can be thought of as equal to all the or the product of all the moduli save small m sub 1. This is equal to, we know that the moduli are 3, 5, and 7. So we're going to put 3 times 5 times 7 all over the first moduli, which is 3. So if we're going to solve this, 3 times, or we can just actually cancel this 3 here, which leaves us 3 times 7, which is going to give us 35. Big M sub 2 is equal to the product, the big M, save the small m sub 2. So this is equal to 3 times 5 times 7 divided by the small m sub 2, which is 5. So we're just going to cancel this up. 3 times 7 is 21. And the big M sub 3 is just equal to, again, the all of the product, the big M, all over small m sub 3. Let me fit that, small m sub 3, which is equal to, again, 3 times 5 times 7 all over 7. So we can just cancel the 7. Sorry for the very populated um, workspace, which is equal to 3 times 5 is 15. Okay, 15. So therefore, um, big M sub 1 is equal to 35, big M sub 2 is equal to 21, big M sub 3 is equal to 15. Now it's up to us to find the y sub 1, y sub 2, and y sub 3 as stated here um, in the things that we want. So just recall these values, 35, 21, and 15. So we'll be getting then the values of the y sub 1, y sub 2, and y sub 3. So to find y sub 1, y sub 2, and y sub 3, we do this. So y sub 1 is actually the solution. Recall, is the solution of the congruence m sub 1 times y sub 1 is congruent to 1 mod m sub 1. You can see this in the part of the theorem, in the part of the proof of the theorem that states that by corollary 3.1, the general standard is the congruence m sub I, y sub I is congruent to 1 mod m sub I. So we're going to use this mod m sub I, this part. So we're going to use this as our basis for in solving the values of y sub I. Okay, in solving this. So let's have it. Um, so since we know m sub 1 or big M sub 1 is equal to 35, so let's substitute. This becomes 35 times y sub 1 congruent to 1 mod, and we know small m sub 1 is equal to 3. Okay, small m sub 1 is equal to 3. So we want to isolate the y sub 1 to get its value. So mod 3, 35 mod 3 is equal to 2 y sub 1, but 2 is like a difficult number to deal with if we're going to look at our theorem 3.2 and theorem 3.4. But if we're going to look at the congruences, again, we have 0, 1, 2, 3, 4, 5. 5 is even um, not good to use, but we can make use of negative 1, negative 2, and negative 3. This is one equivalence class. So we can make use of negative 1 instead of positive 2 since they're equivalent. So we have negative 1 y sub 1 is congruent to 1 mod 3. Again, recall that we're in the universe of mod 3. So we're in a clock wherein it's only three numbers. So 0, 1, 2, 0, 1, 2, 0, 1, 2, or 1, 2, 3, 1, 2, 3, 1, 2, 3. So with this, we want y sub 1 to be totally positive. So since we have negative 1, what we will do, okay, is multiply this equation by negative 1. So by theorem 3.4 or theorem 3.2, AC, A, if we have A is congruent to B mod, let's call this mod something, a mod N. It's AC is congruent to BC mod N. Okay, so that is we're just multiplying any constant with the both sides of the congruence, it will still be equal. So what we're going to do is to multiply this whole congruence with negative 1, leaving us with negative 1 here, mod 3. Okay, oops, sorry. And what we will have is, so negative 1 times negative 1 is going to give us positive 1. And notice that in the on the right hand side we have negative 1 mod 3, negative 1 mod 3, and we don't like to see negative numbers on the remainders. As we can see, as we will go back to the division algorithm, remainders must be positive. Okay, so since this is negative, we go back to our rules here that, oh, so negative 1 is equal to 2. So why not use 2? So we'll use 2 here. Y sub 1 is going to go into 2 mod 3. Okay, and this is our y sub 1, the value of our y sub 1. So let's get a hold of that. Now what we're going to do is to continue this. This is only for y sub 1. We will also do this with y sub 2. So similarly, we say, similarly, um, we say big M sub 2, y sub 2 is congruent to 1 mod small m sub 2. So this implies that recall our m sub 2. M sub 2 is equal to 21. So what we have is 21. Y sub 2 is congruent to 1 um, mod m sub 2. Our m sub 2 is equal to, what's our m sub 2? 5. It's equal to 5. Okay, so 21 mod 5 is equal to 1 mod 5. Okay, so if you want a proof of this, so we can imagine 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so here's 21. And you can see that in this equivalence class, 21 is going to go into 1. So therefore, we can just delete 21 and make it just 1 congruent to 1 mod 5. And that's the end for our, that's already okay for our second y, for our y sub 2. Finally, um, finally, for our third y sub 3, so we have big M sub 3, y sub 3 is congruent to 1 mod small m sub 3. So this yields us big M sub 3 is equivalent to 15. We don't know y sub 3, so let's copy that. Is congruent to 1 mod m sub 3. M sub 3 is equal to 7. So put 7 there. If you're going to check again the same analysis that we did here in our second y, we will also do that in our third y. So mod 7, since this is mod 7, and 15, 15 minus 15 divided by 7 will yield us a remainder 1. So that will give us 1. Similarly with our 2. Likewise, you can think of this as 21 divided by 5 is is something is 4 remainder 1. So something remainder 1, so that's why it has a 1 remainder. 15 remain as divided by 7 is 2 remainder 1. So that's there's a 1 there. So we can just put the 1 here in the right hand side and copy it. So this is our third y sub 3. Now finally, using the central limit theorem. Okay, hence, oops, hence by the not sorry Chinese remainder theorem. No, no, Chinese remainder theorem. By the Chinese remainder theorem, my bad. Chinese remainder theorem. What we have, x, the unique solution, is said to be congruent to, okay, the summation of all the a sub I, big M sub I, y sub I, mod big I, big M, for all i's running from 1 to 3, since we have three um, three congruences in this system of linear congruences. So we will be setting up and putting into the values of a, big M, and y sub 1. Okay, so we'll be putting those values there. Okay, so for all the a sub all the a, this is congruent to, let's start with the a sub 1. Um, okay, if you want, let's make it very thorough. A sub 1, big M sub 1, y sub 1, plus a sub 2, big M sub 2, y sub 2, plus a sub 3, big M sub 3, y sub 3, all in the universe of mod M. What's M anyways? M is equal to 3 times, M is equal to 3 times 5 times 7. So what's M? It's the product of all the moduli. So 3 times 5 times 7, 3 times 7 times 5 is 35. Multiply that by 3, that's 9, 15. That's going to give us 105. So it's mod 105. Mod 105. Okay, good, better. So what we need to do is to fill in these values of all the a, the m, big M's, and the y's. So this is congruent to a sub 1 is it's the first. Okay, so it's the a sub 1. Our big M sub 1 is equal to it's equal to, what's the number? Big M sub 1. Here, big M sub 1 is here, 35. You may also check that down below, 35. So we input here 35 times 35. Y sub 1, as we have solved here, is congruent to 2. And we will be putting that there. Okay, that's our Y sub 1, congruent to 2. Okay, next is our A sub 2, that's the second one, times our M sub 2. M sub 2 is equal to 21, as you can see here. Input 21. Y sub 2 is equal to positive 1 here, congruent to positive 1, so put positive 1 there. A sub 3 is a 3, this is the third one. So M sub 3 is equal to 15, as we have solved, so times 15. And Y sub 3 is just equal to 1. So we put times 1 here. All in the universe of mod 105, the big M. So we continue in this manner by solving. So we have 35 times 2 is going to give us 1 times 35 times 2. So 35 times 2 in short is going to give us 70, plus 21 times 2 times 1 is going to give us 42, plus 3 times 15 is going to give us 45, um, mod 105. So this is arithmetic right now. So this is congruent to 70 plus 42 plus 45. This is going to give us what? 8, 8, 7, 15, 157. So 157, we divide 105 by that, and the remainder is ours. So 105 is going to give us 52. So this is going to give, let's write it if you want, 157 mod 105. So get the remainder. put this in the least residue. So this becomes 52 mod 105. And this is the value of our x. Oops, this is the value of our x. Okay, so this is the value of our x via the Chinese Remainder Theorem. So therefore we say, so since this is the value of our x, um, can we delete this stuff? Okay, I think not. So therefore we say that 52 is the unique solution for the linear system modulo 105. Is, oops, sorry, is the unique solution of the linear system modulo 105. So thus the general solution. So therefore, using this and converting this by theorem 3.1, um, the general solution, thus the general solution is equal to, using again the theorem 3.1, converting this into an equality. So we have x is equal to 105 is the mod, so that's one of the factors of the quotient. It is the divisor, so we have a quotient which is we'll call t, plus 52. This is also equal to x is equal to 52 if you really want to follow the the ordering of the theorem. 52 plus 105 plus 105t. And that ends our solution. This is the general solution for this example for Sun-Tzu's problem. Okay, so that's it for this video. I hope you learned something from that. I'm going to give another example for the Chinese Remainder Theorem in the next video. So kindly hit the like button and subscribe also. So thank you very much.